Everybody, welcome to Please Inject Me, x64 code injection. So let's start. A little bit about me. My name is Alon. Been to the cybersecurity industry for about 7 years. Started at the IDF in the intelligence division, and now working at Deep Instinct. At Deep Instinct, I'm researching for new attack vectors, doing some heuristics, and finding new ways to attack, also reversing malwares. So that's pretty much about me. Okay, so in this talk, first I'm going to give you a short introduction about code injection, so it's going to be really short. I'm going to talk about what is Inject-Me, the new code injection technique I found. Then I'm going to give you a little bit of a technical background just to know things that you need to know before you can abuse the method to do the code injection. And at the end, there's going to be a detailed flow of how to do the code injection. Okay, so what is code injection? Code injection is the term of inserting code from one process to another and then execute it in the context of the other process. So it looks like this. First, we inject code to the target process, message box, and then we execute the code. Okay, so through this presentation, I'm going to use the terms target process and injecting process. Okay, amazing. Okay, so why code injection is important? Okay, code injection is important because it can be used for malicious and benign activities. Okay, so it can be used for malicious activities like for stealth. Okay, if a malware author wants to hide the presence of the malware and make it harder to find it, it can inject the code into another process and then it will be hard to detect it. It can be used for evasion, so we can inject into a security solution, okay, and then we can bypass that security solution, but if we inject into the solution, they won't scan the activity of the malware. We can also, if let's say only one program is allowed to do something and we inject to that program, we're going to be running in that context and then we can use the context to do something malicious and bypass the security solution. And at the end, we can steal information, let's say phone grabbing in browsers, and then we can see credit cards, data and things like that. For benign users, we can use it to, in security solutions, we can use it to get the activity of a malware, okay? And the malware, we can see what it does, and if it does something malicious, we can just inform the user and tell him that something bad happened. Also, it can be used to add some functionality to a program, so we can add something new that is not written in the code. And at the end, we can also do some monitoring, so a security researcher can monitor the activity of a malware and then see what's going on. It's not only a malware, it can be for any program. Okay, so how it all started. I was researching a few methods of code injection to do heuristics, and then I thought to myself, why wouldn't I do my own code injection technique? Maybe I should look for it. So I thought a little bit about it and I had an idea. Lucky for me it worked, the idea that I'm presenting today. So this new method is going to be used in x64, okay? The idea behind it is we are going to use ReadProcessMemory in the target process. It's going to execute ReadProcessMemory and then read from the injecting process, the shellcode. This one I'm going to use the term injectionness because we really not really injecting code into the target process, we make it read from us. Amazing. Okay, so now a little bit of technical background. ReadProcessMemory, a WinAPI function in Windows. This function, what it does, it just reads data from a process. It gets 5 parameters, H process, which is going to be the process we want to read from, LP base address, which is the address we want to read from, okay, LP buffer, which is the address we want to write the data we read to, and n size is going to be the size we want to read, and LP number of bytes is going to be the number of bytes that were actually read. Okay, now x64 calling convention. In x64 calling convention, the parameters are passed on the registers. So they are passed at RCX, RDX, R8, and R9. We can pass these 4 parameter arguments to a function, and then when we execute it, the function is going to use those arguments. Arguments after the 4th parameter are passed on the stack. So if you see at this diagram here, you can see that if we call ReadProcessMemory, R6 is going to be the H process, RD is going to be the LP base address, R8 is going to be LP buffer, R9 is going to be N size, and then LP number of bytes is going to be on the stack. So if we look at the stack, the return address is going to be at the top of the stack. Then there are 4 arguments that are ignored. The data there is not important. And then at the end there's going to be the 5th parameter at the stack. So again, if we use setPredContext, the function, and set those registers, we can just manipulate a function to execute with those parameters. Okay, so through this presentation you're going to see this timeline. It's going to show us where we are. First we're going to talk about how to set up ReadProcessMemory. Then we're going to encounter the first problem, which is access violation. We'll then encounter another problem that we will need to create an infinite running thread. And at the end we're going to execute the whole method. Okay, so let's start. ReadProcessMemory. Okay, as I showed you earlier, it gets 5 arguments. Okay, and as I already told you also, we can only pass 4 arguments using the registers. Now, lucky for us, the 5th parameter can be null, then it is ignored. And more lucky for us, if you use virtual alloc EX, the allocated memory is going to be all zeroed out. So we can create a dummy stack that is going to contain the 5th argument. So this is good for us. Okay, so let's start setting up ReadProcessMemory. So the first parameter we need to set up is H process. Okay, H process we can set it up by using duplicate handle. So we're going to duplicate the handle of the injecting process into the target process, and then we have the handle inside the target process. We can use it as H process. Then we will allocate memory for our shellcode. Okay. The dummy stack we already allocated earlier. The base address of the shellcode we already know because it's in the injecting process. And the size of the shellcode we already know because it's also something we know in the injecting process. Okay, so let's say now that we actually called and executed ReadProcessMemory. We are going to execute it and we are going to have our first problem, which is access violation. So what's going to happen is we first call ReadProcessMemory. The memory is read to the buffer, and then we go to the return address. Now, because the stack is all zeroed out, we are going to return to the address 0, which is invalid. And we're going to get access violation. Not nice. But if we put as the return address a function like RTL exit user thread, we just exit the thread in a clean way. When we'll execute ReadProcessMemory, it will be called, memory is read to the buffer, we return to the address on the stack, and the thread will execute in a clean way. Amazing. Okay, now we want RTL exit user thread to be on the return address in the stack. Okay, so to do this we have 2 steps. First we need to find a place where RTL exit user thread address exists. Okay, so let's first talk about kernel 32 and NTDLL. Okay, those are both DLLs in Windows that are loaded in each process at the same location. So the base address of them is similar in each and every process. And kernel 32 also imports the function RTL exit user thread from NTDLL. So what this means is if we look at the import address table and we find in our version, in the injecting process version, the address of RTL exit user thread in the IAT, it's going to be at the same place in the target process. So we can copy that there using a method I'm going to describe right now. Okay, so to copy the address, we're going to use the function ntqu apc thread. Okay, this function gets a thread handle which we want to execute our code in that thread. Then it gets the function we want to execute, and we are allowed to pass 3 arguments. Okay, so we are going to use the function RTL copy memory. Okay, give it destination, source, and length. Then the target process is going to execute RT copy memory. Now the destination is going to be the return address of our dummy stack. The source is going to be the address of RTL exit user thread in our version of kernel 32 IAT, and the length is going to be 8 bytes, which is the size of a pointer in x64. Okay, now a little side note. We can use this method of copying, okay? We can use it to recreate a shellcode. So we just need to find in our version of, let's say, NTDLL, the bytes of our shellcode one by one, and then we can just copy it in the target process, and we can just recreate the shellcode there. Okay, now let's finalize the execution. So my first idea was to set RIP to read process memory, set all the other registers, and then just execute it. But the truth, when you do so, you do it on a suspended thread, and then you resume it, you get the exception status invalid parameter. And we don't want that because that makes the process crash, and even if something happened, it just will crash and won't work. And if we want to do something with a thread, we want to do something to copy to read process memory, we need the thread to initialize before we can manipulate it. Okay? Another thing, if we'll start a thread and it won't be suspended, it will just run, terminate before we can manipulate it, and that will be bad for us because we won't have time to do our stuff. So to do it, we need to create an infinitely running thread. We'll create that thread, and then we'll manipulate it to run read process memory. Okay, so when create remote thread is called, the first function that's going to execute is RTL user thread start. This function first called to a function. After that, you just do other stuff, and then does jump RBX, which is going to be the entry point you deliver to create remote thread or create thread or whatever. And I guess you haven't seen it, but RBX was never used here. RBX was never changed during this time. So we are going to abuse that, and we are going to use the opcode jump RBX to do the infinitely running thread. So what we're going to do is we're going to allocate memory for jump RBX. Then we will look for jump RBX opcode in our NTDLL version in the injecting process. We will copy it using the method described earlier to the target process. Then we'll create a remote thread that is suspended, and it's going to point to the jump RBX that we just copied. Then using set thread context, we are going to set RBX to point to jump RBX, and then resume the thread. So now what's going to happen is going to execute, get to the jump RBX we talked about earlier, and then this is going to jump to the jump RBX. RBX points to the same location, so it's just going to jump over and over and over and over and over again. And that's how you make it run infinitely. Okay, so now let's execute the code. Let's just execute the code injection. So now we will suspend the thread and see that the RIP really points to our jump RBX opcode, so we know that the thread was initialized and everything is okay. And then we'll start setting the thread. Okay, so RCX is going to point to the duplicated handle we duplicated. RDX is going to point to the address of the shellcode in the injecting process. The buffer, the LP buffer, which is R8, going to point to the location we allocated for the shellcode. R9, which is the size, is going to be where we the size of the shellcode. Then RSP is going to point to the dummy stack we allocated, so the fifth parameter will be null. And RBX is going to point to ReadProcessMemory. So when we are going to resume the thread, jump RBX is going to jump to ReadProcessMemory. All the other parameters are already set up. So we're going to do that. We'll call wait for single object just to see that the thread was finished. When it's done, the shellcode is already copied into the target process. And now all we have to do is just use a function like create a mod thread and execute the shellcode. So now for demo. So in this demo, I'm going to open a notepad, execute the code injection method, and you're going to see at the notepad the command line in a message box, of course, the command line of the notepad that we opened. So here I open the notepad, please inject me. We start running the program. We duplicate the handle of our process to remote one. We allocated memory for shellcode. Then we allocate memory for our dummy stack. We will find RTL exit user thread and copy it to the dummy stack. We will allocate memory for jump RBX. We will copy jump RBX into the allocated memory, find ReadProcessMemory. Then we'll create a remote thread that point to jump RBX. We'll set the thread context. Context was changed. We will execute ReadProcessMemory. And now execute the shellcode. And when you look at the notepad, you can see the message box with the command line. So thank you very much for having me. I hope you enjoyed the talk. Special thanks for Maddie Stone for helping me doing it. The white paper is going to be published in the next few days. It's still not up, but you're more welcome to ask any questions. If I have time, I think I have. Thank you. Are there any questions? Okay. Okay, thank you very much.